motion in vertical circular path. An object tied with a string rotating in a vertical circular path. Suppose this is horizontal line, and when particle is at a point where it makes theta degree with the horizontal. Now, if its tangential velocity be v tangential is the tangential velocity of the particle, therefore its omega, that is angular speed, is equal to v by v tangential divided by r. R is the radius of the circular path. Therefore, if we consider non-inertial reference frame, that is moving with circular path, that is accelerated reference frame, so object at this path experience a pseudo force, which is centrifugal force, away from the center, and that is equal to m v square by r. This is tangential velocity, that is vt, okay? And that due to the non-inertial reference frame, and a tension T which keep the body in circular path be T. Now, the weight of the body acts vertically downward. This is mg, vertically downward. So, if we resolute this force in mutually perpendicular direction along OB and perpendicular to OB, that is opposite to the VT, just in tangential direction, it is clear from the figure that if this is theta, then it should be theta. So, this is mg cos theta, and this will be mg sin theta. So, we can say that T plus mg sin theta is equal to m v square by r. This is a general expression for tension. Tension is equal to mv square by r minus mg sin theta. When theta is equal to 90, T is equal to mv square by r minus mg, because sin 90 degree is equal to 1. Therefore, T minimum, this is T minimum, minimum tension is equal to m v square by r minus mg. To maintain circular motion, to cover that whole path, T should be greater than 0. T should be greater than or equal to 0. The minimum value, that should be 0. So, we can say that v square by r should be greater than or equal to mg. So, v greater than or equal to root over rg. So minimum velocity, tangential velocity, that should maintain to complete the circular path. This is very important relation. When theta is equal to 270 degree, sin theta is equal to -1. So tension is equal to mv square by r plus mg. So tension maximum, T max, will be this when it is given that the maximum permissible tension of the string is this value. So we have to equate this mv square by r plus mg should be less than or equal to maximum permissible tension. This expression is important. And this is also important. And this is. Now, if we consider this part of the force, mg cos theta, acts against tangential velocity. So, retardation of the object is equal to g cos theta. Now, suppose a pendulum or any object hanging from a fixed point, and at the bottommost position a velocity is imparted along tangent direction to the body bb. And what will be the velocity of the body when it makes theta degree with the initial bottom position? Suppose this is a, and suppose this is theta. Now, at this position, gain of potential energy is equal to mgh. Here kinetic energy at this point is equal to half mv b square, or simply v square. I am considering this is v0, okay, b0 square, that is initial. With respect to reference point, if it raises its height, then potential energy will gain by the body and kinetic energy loses. Now, at this point, at any point, its velocity be v, tangential velocity obviously, and this is theta, and this is r, that means radius or radius of the circular path. So this also r, and if it is o, it is a, this is b, and the perpendicular from b on oa is c, then we can say that OC is equal to r, OC is equal to r cos theta. So the height AC is equal to r minus r cos theta, that is r into 1 minus cos theta, that can be written as r into 2 sin square theta by 2. 1 minus cos theta is equal to 2 sin square theta by 2. Gain of potential energy, gain of potential energy is equal to mgh, that is 2r sin square theta by 2. Therefore, the kinetic energy at point B, K at B, is equal to K at A minus this, that is 2 mg r sin square theta by 2. Kb is equal to half m v square. V, that is velocity at any point when it makes theta degree, and this is half m v0 square, that is initial kinetic energy, minus 2 mg r sin square theta by 2. So v square is equal to v0 square minus 4 rg sin square theta by 2. So v is equal to root over minus 4 rg sin square theta by 2. This is very important formula for joint entrance. Now when theta is equal to 180 degree, when theta is equal to 180 degree, it will be at the topmost position, like this.
Theta is equal to 180 degrees.
And from, if you calculate angle from this bottom point, so theta will be 180 degree when it is at the top point. So velocity at the top is equal to root over v0 square minus 4rg theta by 2, 180 by 2, that is 90 degree, that is 1. When theta is equal to 180 degree, velocity at the top. And we know that at the top position, minimum velocity required is equal to root over rg to continue vertical circular path. So for minimum velocity by speed at top, minimum velocity at top is equal to root over rg. Root over rg is equal to root over v square minus 4rg. rg is equal to v0 square minus 4rg. rg, therefore v0 square is equal to 5rg. v0 is equal to root over 5rg. So to maintain a vertical circular path, the velocity at the bottommost position should be root over 5rg.
Bottommost position.
Bottommost v0 is the velocity at the bottommost position, that is tangential velocity at the bottommost position. This is very important relation for joint entrance. So at the top, root over rg, minimum velocity. To maintain that minimum velocity, at the top, body should have velocity of root over 5 at the bottommost position. And also we can calculate the tension at various position by using this relation and the above relation. But theta is different. Here theta is from the bottom and it is from x-axis. So the difference of the theta is 90 degree to this theta and this theta. Before starting circular mechanics, now I am discussing about the similarities between circular motion and the linear motion. Okay? And circular motion. First, number one, displacement. This is angular displacement. Displacement is symbolized by S and this by theta. Initial velocity. This is U initial. Number two, angular speed, omega 0. Third, final velocity, V, final angular speed, omega. Fourth, acceleration is equal to dv dt, and angular acceleration symbolized by alpha, and that is equal to d omega dt. 5, formula V is equal to U plus AT. Omega is equal to omega 0 plus alpha t. Number 6, S is equal to ut plus half AT square. Theta is equal to omega 0 t plus half alpha t square. 7, V square is equal to U square plus 2as. Omega square is equal to omega 0 square, that is initial angular speed, plus 2 alpha into theta. Force F, torque. We will discuss relation between force and torque later, but the term force can be substituted by torque in case of angular or circular motion, and torque is symbolized by tau. This is like T but slightly different. 9, inertia. Inertia, we know that in case of linear motion, mass is the measure of inertia, so we always express inertia by mass, symbol m. Moment of inertia, symbolized by I. We will discuss about this in details in circular mechanics. 10, momentum. We know that this is symbolized by P, and it is product of mass and velocity. Angular momentum, that is symbolized by L. This is also vector quantity and is I into omega. By changing inertia to moment of inertia and force to torque. So in first law, it is given that if there is no external unbalanced force acting on a system of bodies, body remains in a state of rest or of uniform motion in straight line. So it can be converted if there is no external torque, force should be replaced by torque. If there is no external torque acting on a system of rotating masses, then system will continue its motion in uniform circular path. And second law, rate of change of momentum is directly proportional to the applied force. Here it will be rate of change of angular momentum will be directly proportional to the torque. So momentum converted into angular momentum. What is angular momentum? Angular momentum, and this is moment of inertia I, and this is tau, like t, it's a curve. Is a vector quantity, is a scalar quantity. Now angular momentum is equal to I into omega, just like m into v. M is replaced by I and v is replaced by omega. This is called L. So dl dt, rate of change of momentum, is equal to I into d omega dt. Rate of change of angular speed, that is equal to angular acceleration alpha. Alpha is equal to angular acceleration. Now, what is the relation between angular acceleration and linear acceleration? We know that tangential velocity Vt is equal to omega cross r. Vt is equal to. Now, this is tangential velocity. If this tangential velocity changes its magnitude, that is dvt dt is equal to d omega dt cross r. So tangential acceleration is equal to angular acceleration cross r. Now if we apply second law of motion in circular frame, then dl dt, that is rate of change of angular momentum, is directly proportional to the external unbalanced torque. So we can write it T is equal to I into alpha, that is F is equal to m into A, same relation. Now what is torque? Torque is a vector quantity and it is axial vector, and the direction of the torque is along the direction of the angular acceleration. Both are axial vector. On which factors magnitude of the torque depends. It is clear that whenever we try to change the angular speed of any rotating object, then we have to apply torque. Now, in our daily experience, we observe that suppose this is hinge of the door and this is a door. If we apply a force at the free end, it requires less force to rotate it. If we apply force that is closer to the axis of the rotation, we need greater force. Same torque, same effect we'll get with less effort, that is applied force, when we increase the distance of application of the force from the axis of rotation. So we can say that torque is directly proportional to the R, that is R is the distance of the point of application of force from axis of rotation. Axis of rotation. So tau torque is equal to R into F. If the point of application of the force is closer to the axis, we have to increase the force to get the same effect. So we can say that torque is the product of R and F. Now torque is a vector quantity, R is a vector quantity, F is also vector quantity. The relation among this, tau is equal to R cross F. Now if you substitute this part, so tau is equal to R into F is equal to I alpha. Alpha is equal to tangential acceleration divided by R, because tangential acceleration is equal to alpha into R, and F is equal to m into tangential acceleration is equal to I into a tangential divided by R. So tangential acceleration cancelled. Sorry, this is R and this is ma. F is equal to ma. So I is equal to mr square. Now finally we have got the relation among moment of inertia, mass and R. So it is clear that inertia, in case of linear motion, inertia is the inherent property of the material that never depends on any external factor. But moment of inertia depends on the R. R, that is distance of the mass from axis of rotation. R, that is distance of the mass from axis of rotation. Now, considering a body is rotating about this axis, and this is the body, and it is rotated about this axis. So different masses are at different distance from the axis of rotation. That body consists of infinite numbers of point masses, and all masses has specific distance from axis of rotation. Suppose this is R1 and mass M1, R2 mass M2, R3 mass M3, and so on. So moment of inertia of this body I can be written as M1 R1 square plus M2 R2 square plus M3 R3 square and so on. So I can be written as sigma, that is summation of Mi Ri square I for 1, 2, 3, 4. Now in case of linear motion, we always take a point which represents the whole body. Suppose in case of this block, when we study the motion of this block, we just take the CG of the body and observe the motion of the body. That is a rigid body. As the inertia of the body is inherent property of the material, and it never depends on external factors, so it remains constant. But in case of moment of inertia, this changes with the point and also position of the axis, internal and external factor. Now the sum of the point masses, that is sigma m, is equal to mass of the object and the point which can represent the whole body. That is, if we consider a point and mass of that point is m, capital M, which is sum of all the masses, and rotating about the same axis, the radius, that is distance of the point from the axis, be k. So mk square is equal to sigma mi square. So k square is equal to sigma mi square divided by sigma mi, that is I by m. K is equal to root over I by m. This k is called radius of gyration. Radius of gyration. Now, if axis of rotation be the centroidal axis of the body, that means this is a centroid or center of mass, and axis passing through this point, this is called centroidal axis. If the body rotates with respect to that centroidal axis, then its moment of inertia is called Ig. Moment of inertia about centroidal axis. This is the moment of inertia about centroidal axis. This is constant, Ig is constant for a given figure, because centroid of the body is a fixed point. So all the masses about this line will be evenly distributed in both the sides. Now this is the body, and it is a centroidal axis, and moment of inertia of the body when it rotates about this axis be Ig. Now if we move this axis to a distance h from it, then what will be its moment of inertia? This is, say, I. Now we are considering an arbitrary point on the body which is at a y distance from centroidal axis, and it will be y plus h distance from this axis. Therefore this is y distance or x distance, x in this direction, so it is x, this is x distance, and this is x plus h distance. Now moment of inertia of this body I is equal to sigma m into x plus h whole square, m r square, is equal to sigma m x square plus 2xh plus h square is equal to sigma m x square plus 2 and h are constant, so 2h sigma m mx plus h square into sigma m mx square, that is moment of inertia about centroidal axis Ig, plus mx square, moment of mass about centroidal axis, because x is distance from the centroidal axis, and we know that all masses are evenly distributed over this centroidal axis. So net moment of the mass about centroidal axis is equal to 0. So 2h into 0 plus h square sigma m, that is sum of all the point masses, which is equal to mass of the body, Ig plus m h square. This is called parallel axis theorem. Parallel axis theorem. Now suppose this is x axis, this is y axis, and this is z axis, and the body belongs to this xy plane. If you consider a point on the body, this is x axis, y axis, and z axis. Now distance of the point from x axis, if we draw a line parallel to y axis, that will be this is the distance of point from x axis, which is equal to y coordinate of the point, and distance from y axis is equal to, this line is parallel to x axis. So if the body rotates about x axis, then moment of inertia Ix is equal to, that is distance from x-axis, sigma m y square. When it rotates about y-axis, Iy is equal to distance of the point from y-axis, that is x coordinate, sigma m x square. Now what will be the distance of this point from z-axis? This is the distance of the point from z-axis. Distance of the point from z-axis is this. Now this is parallel to y-axis and this is parallel to x-axis. So they are perpendicular to each other. So this is a right angle triangle of which r, that is the distance from the z-axis, r hypotenuse. So r square can be written as x square plus y square. Sigma r square, sigma mr square is equal to sigma m x square plus y square is equal to sigma m x square plus sigma m y square. That is, this is called Iz. So Iz is equal to Ix plus Iy. This is called polar moment of inertia. When axis of rotation normal to the plane, this is normal to this plane, but this axis and this axis belongs to that plane. Moment of inertia of rectangular figure. This is a rectangle and its CG passing through middle of this. Now, if you consider an elementary area, this is an elementary area at a distance y from central axis and its thickness is dy. This is dy. This is uniform lamina, therefore its mass uniformly distributed over the area and mass is proportional to the area. Let this is B, width of the lamina B, and this is length L. This is B. M be the mass of the figure. Therefore, mass per unit area is equal to M by L into B. So del A, area of the elementary part is equal to del A is equal to L remains same, L into dy. So mass is equal to del M is equal to L dy into m by lb. So L cancelled is equal to m into dy by b. Now moment of inertia of the elementary mass is equal to del I is equal to m dy by b. This is mass into r square, that is y square. So I is equal to m by b integration y square. This is y will be from 0 to b by 2 and here minus b by 2. So y will be minus b by 2 plus b by 2. Minus b by 2 to plus b by 2 into dy is equal to m by b y cube by 3 minus b by 2 to plus b by 2 is equal to m by b into 3. This is b cube by 8 plus b cube by 8 is equal to m b square by 12. That is 1 by 12 m b square. Conservation of linear momentum, law of conservation of linear momentum. We have got that from Newton's third law of motion, that initial total momentum will be equal to final total momentum if there is no external force acting on the system. In case of rotational mechanics, we can write it sigma I into omega, that is equal to constant if there is no external torque acting on the system of the rotating masses. It has so many applications. That is, when you stretch your hand during rotation, the angular speed reduces. If you close your hand towards your body, your angular speed increases. During somersaults, that is jumping over on the leg, if you close your leg towards your body, then your spinning increases, and if you stretch your leg and hand away from the body center, then your rotation will be reduced. These all are example of conservation of angular momentum.